You were asking about this problem, and this is a rational inequality, so we have to get 0 on one side. So I'm going to take this 6 over 5x squared plus 1 to the left side. So I got 2 over x squared plus 7 minus 6 over 5x squared plus 21 is greater than 0. Now normally we would factor the denominators to help us figure out what the LCM of the two denominators are, or LCD, but these do not factor. So our LCD will just be the two multiplied together. So we'll have x squared plus 7 times 5x squared plus 21. And same thing here. Well, you have to figure out what did you multiply by the bottom. So for our first denominator here, it had an x squared plus 7. That x squared plus 7 is still there. The new item we put down there is 5x squared plus 21. So whatever new item we put down below, we have to put up on top. The mathematical principle behind that is whatever you multiply by the denominator, you multiply by the numerator. In our second fraction, it had 5x squared plus 21, which is still there. The new item is the x squared plus 7. And again, whatever new item you put down below, you had to put up on top. Is greater than 0. 2 times 5 gives us 10x squared. 2 times 21 is 42. Over x squared plus 7. 5x squared plus 21. Minus 6 times x squared is 6x squared. 6 times 7 is 42. Over our denominator. Now since they have the same denominator, I'll merge together the top parts. Remembering if you got a minus in front of your fraction, that flips the sign of everything up on top. So we're going to have 10x squared plus 42 minus 6x squared minus 42 over x squared plus 7 times 5x squared plus 21 is greater than 0. 10x squared minus 6x squared is 4x squared. 42 minus 42 drops away over the denominator. Okay, we got our single fraction. That's our goal. You can't solve rational inequality if it's not a single fraction. So what we're going to do is, since we can't factor the same more than it's already factored, we'll set each factor equal to 0. So I'll set 4x squared equal to 0. I'll set x squared plus 7 equal to 0. And I'll set 5x squared plus 21 equal to 0. Now here, whenever you have a single x to a power number in front of it, that just simply gives you 0. Reason why is if I divide both sides by 4, I get x squared equals 0. If I drop the squared and put a plus or minus square root on the other side, well, square root of 0 is 0, and a plus or minus 0 is just 0. It always works out that way. Now here I'll take the 7 over, it becomes a negative 7. And we apply the square root property. We drop our squared and we put a plus or minus square root around the other side. A negative inside of your square root, though, gives you an imaginary number. And we can't have imaginary numbers in our critical values. Now here I'll take the 21 over. Divide both sides by 5 because we have to get the part that's squared by itself. Drop the squared and put a plus or minus square root around the other side. And we got the same problem. We got a negative inside of a square root, which gives us an imaginary number. So that's going to drop away. So we only have one critical value, x equals 0. So we're going to build a table of intervals. Here's negative infinity, here's positive infinity, and here's 0 in the middle. We want to choose test cases. I want to choose something between negative infinity and 0, like negative 1. It does not matter what value you picked, as long as it's between negative infinity and 0. And then I want to pick something between 0 and positive infinity, like 1, or 2, or 3, or 1 million. Doesn't matter what you pick. Now we're going to plug those in to this point right here. So we're going to have 4 times negative 1 squared over negative 1 squared plus 7, and then 5 times negative 1 squared plus 21, and greater than 0. And this is a question mark. We're wondering if it's greater than 0. Negative 1 squared is positive 1 times 4 is 4. Negative 1 squared is positive 1 plus 7 is 8. Negative 1 squared is 1 times 5 is 5 plus 21 is 26, I think. Now we really don't care what this value is equal to. We're just checking to see if it's greater than 0. And 4 is positive, 8 times 26 is positive. So I don't know what this is equal to, but it's a positive number because positive divided by positive is positive, which is definitely greater than 0, which means this interval is true. Now we want to plug in 4 also. So put 4 in, or 4, 1. And then we got 1 squared plus 7. And then we got 5 times 1 squared plus 21. We're wondering if that's greater than 0. 1 squared is 1 times 4 is 4. 1 squared is 1 plus 7 is 8. 1 squared is 1 times 5 is 5 plus 21 is 26. And we're wondering if that's greater than 0, which it is. Okay, so it's true in this interval, it's true in this interval. So this interval is from negative infinity to 0. And this interval is 0 to positive infinity. Now these have parentheses on them because this is a greater than. Now actually, if this had been a greater than or equal to, what you would have found is that your answer would have been negative infinity, positive infinity, because it would have included the 0. But this right here says to exclude the 0. Now that's how you can use test cases to check it. You can also look at the graph. And the trick is, once you got a single fraction, you put parentheses around the top, parentheses around the bottom. And let me plug that in. So beginning parentheses 4x squared, closing parentheses divided by beginning parentheses, that's this blue one. Then I want another beginning parentheses for the x squared plus 7. Closing parentheses for the x squared plus 7, beginning parentheses for the 5x squared plus 21. And you don't need the closing parentheses at the very end unless you just want to put them. But I'll press graph. Now I'm not seeing anything, but I should see something that's 0, so it probably means that I need to zoom. Sometimes it's not so easy to do these on the calculator. If I do zoom and choose zoom out, 3, and press enter, and I still not seeing anything. Maybe I need to zoom in. Let me press enter one more time. Okay, nothing. So let me do a zoom 6. And now go back to zoom 6, sets back to standard viewing window. Now do zoom, choose zoom in. And then I'll press enter one time. Press it one more time. Zoom in by another factor. You have to wait till it comes back. See the little dash going upper right. If you don't wait till it comes back, it gives you an error. And one more time. I'm just not having any luck seeing anything. 4x squared divided by x squared plus 7, 5x squared plus 21. Now if I set my table setting, so if I go to second window and then down arrow to independent and choose ask, Mine's already chose, but yours probably says auto. If you right arrow over and press enter on ask, and then exit out, second mode. Now if you go to your table, you do second graph, you'll be able to enter in values. For example, we had a test case of -1. I put in -1, press enter, and I can put 1 in and press enter. And see how they both come up as positive? That's what we just said right here. They're both greater than 0. Doesn't look like with this one we can actually see the graph. I don't know where it's exactly at. Could be it's so small because these values. Let's try -3. See what we get. Yeah, it's super small. See how that's 0.03 now? Maybe if I set my Windows settings, I came here and I put in I don't know, -3 to 3, and then change my Y-min to -0.9. Just guessing, and then 0.9 for the max. Actually, look like I can see it a little bit better the other way. Let's set this to -0.5. And put in 0.5 there. Then if I press graph, I can see it a little bit. Those are actually a little bit easier to see graph-wise than they are doing it by hand. I did it by the test case here because I wasn't sure how you were going to do it. But even if you use test cases, if you use the table feature, that really does save you a lot of time. Now, whatever zooming you've done, press zoom in 6, and that should set it back to your standard viewing window. Now I had 0 on Y2 there. You didn't actually need 0 on Y2 there.